Right, so here is a Mega Beast, so a multi-step calculation. You can see it's worth 6 marks and it involves moments. So, figure 2 shows how a small weight placed on an insulating bar makes the wire X go back and balance its original position. So normally if the magnet wasn't there, okay, it would just fall, but the magnet is pushing up on it, which is holding it in a balanced position. Okay, and because it's balanced, that means the moment that way, which is clockwise, so we can say that's a clockwise moment, must be equal to the anti-clockwise moment, which is there. Okay, now straight away it says the wire X is 5 centimeters long and carries a current of 1.5 amps. So straight away that needs to be converted because it's centimeters. That doesn't, that's fine. That doesn't, because that's got Newton meters and that's what it's meant to be. And this needs to be inverted because it's 8 centimeters. And to convert centimeters to meters, what you do is you divide by 100. Okay, so we'll do that in a minute. So first of all, we're going to see phi for it. So it's asking us to work out magnetic flux density. So as a result, okay, we need to write down the equation for magnetic flux density that you can get on your equation sheet. That is force equals magnetic flux density times current times length. Okay, so B equals magnetic flux density, I equals current, and we know that L equals length. I'll put it down anyway because it's only a little word, length, and then F equals force. So what we're going to do is we insert the numbers that we know. Okay, so we don't know the force, there's nothing there to tell us what the force is. Okay, so that's a mystery. We do not know what the magnetic flux density is because that's the thing that we're trying to work out. Okay, so I underline that twice because that's the thing that we're trying to work out. Okay, right, we know the current is 1.5 because it says it there, and we know that the length of the wire, okay, yeah, is 5 centimeters long. Okay, so the wire X is 5 centimeters long and carries the current of 1.5 amps. Okay, so that means 5 centimeters, but 5 divided by 100 to get it into meters, which is 0.05. Okay, so we now know that length is 0.05, but now we need F. F's missing. But we're given the moment, so it's going to be pretty obvious that we're going to use moment. So what we do is we see phi for again. I'm going to use our equation for moment. Okay, we do need to convert because we need that distance for moment. So that is 8 divided by 100 because we're going from centimeters gives us 0.08. Okay, that's 0.08 meters. There. Now we need to get our moment equation. So moment equals force times distance. Now we know our moment. Okay, our moment is that. So it's 4.8 times by 10 to the minus 4 equals our force, which we're trying to work out. We're trying to get that just there. Okay, and we want our distance, which we know is 8, which we've already converted to 0.08. So now what we've got to do is rearrange that to work out F. So if we rearrange that, we're timesing by F. So if we divide by, so if we're timesing by 0.08, so if we divide by 0.08 on both sides, we get rid of that 0.08 and leave F on its own. So what we end up with is 4.8 times by 10 to the minus 4. Okay, divided by 0.08, that will give us this. So with fraction button for that, so fraction button, then we do 4.8 times by 10 to the minus 4, and then we divide that by 0.08, and we double check that looks right, and we press equals, and that's 6 times 10 to the minus 3. So that means, okay, our force is 6 times 10 to the minus 3, which is a little force, which you'd expect it to be on a wire that's only 5 centimeters long. Okay, so it's 6 times 10 to the minus 3. So we put that into our force there. So we say 6 times 10 to the minus 3 equals B, which is our magnetic flux density, times by 1.5, which you've already got, times by 0.05. Now when we want to get B all on its own, so all we do is we times them by 1.5 and 0.05. So if we divide by those on both sides, that leaves B on its own. So then if we rearrange, that's 6 times 10 to the minus 3 divided by 1.5 times 0.05, that gives us B. And we put that into our calculator. Okay, we get 6 times by 10 to the minus 3, and then we do 1.5 times by 0.05. Double check that looks right. Looks alright to me, and then press equals. Something definitely wasn't right, so let's try that again. 6 times by 10 to the minus 3, and then 1.5 times 0.05 equals 0.08. Okay, so the answer is 0.08. The magnetic flux density is measured in Teslas. Okay, it's measured in Teslas.